Good Thursday afternoon, everyone. Welcome to Mathematics for Construction, right? Lecture 21. Last lecture, we had a homework question. Show that the equation is dimensionally consistent, meaning the dimensions on the left is equal to the dimensions on the right. Okay, so dimensional analysis, we could use it several ways. One is to show that formulas are dimensionally consistent. But what we really want to use it for is to figure out what a formula might be, right? Not necessarily prove a formula, but get very far into determining what the formula might look like, you know? So here we say we're using it for the easy case, which is to show you're given a formula already, and you have to show that it's dimensionally consistent. So the first step is, you replace each quantity in equation with their dimensions in square brackets. Okay. So we have here, S. What is S? S is distance or displacement, right? I said distance is meters, right? So dimensions of S would be L, okay? That's the dimension of S, because we saw here in the table, the dimension for length, anything measured in meters, right? Not necessarily length, but it could be perimeter, right? Perimeter is a distance measurement. It's not a basic quantity, but perimeter will be measured in meters. So the dimension is L. Acceleration, right? What is acceleration? So you're given this here, A. Now, this is meter per second squared. So that's L. And we have a second, right? That's time. So that's T to the power -2, right? So that's the dimensions of acceleration, not the units. These are the units here. But what we do, we replace the units, the SI units, with the dimensions in square brackets. Okay. And what is T? Dimensions of T. Okay. Dimensions of T. Well, sorry, T. Now the variable T, it is time, which is measured in seconds. So the units is seconds, but the dimensions is T, right? So that's T. So when we look at the formula there, we had to look at the left-hand side. Left-hand side has dimensions, which is just L. The left-hand side is just dimensions L. Over the right-hand side now. Right-hand side has dimensions. We substitute for these variables here, S, A, and T into A and T, the right-hand side of the formula. So look at the formula, we're looking at the right-hand side of the formula, and we substitute in the dimensions for the variables, right? So what we have A times T squared. So we have A times T squared, right? But this is the right hand. Forget about the 2. The 2 is a constant that has no dimensions, that's dimensionless. So we substitute for the A here. Take this. That is the A here, right? times t squared. So what's the dimension of t? Turns out to be capital T. Like that, right? So our right-hand side has these dimensions. So you just want to simplify this here. What is this? L t to the minus 2, the t is raised to the power minus 2, right? So you'll have L in the numerator, and you just have a t squared in the denominator, right? And we times t squared. And what would happen is they will cancel, right? They would cancel to give L. So the dimensions of the left-hand side is equal to the dimensions of the right-hand side, okay? That's what we say here. The dimensions of both sides are the same. So the equation is dimensionally consistent, okay? And that's basically what is involved in taking an equation, right? Finding the dimensions of the symbols or the variables in the equation. That's what we did here, right? You look at the equation, and for each letter, what is that dimension? And what would help you with that is the units. Usually they'll give you the SI units of each symbol, right? And you use the units, which should be SI units, right? You use those units to figure out what the dimension of each of the variable is. And then you plug the dimension into the formula, and you try to simplify and see what it is you end up with. All right, so tidy up the notes a little bit to give you a step-by-step process of how to do this. One use of dimensional analysis is to show that the equation is dimensionally consistent. How do you do this? Let's look at the example. Show the equation E equals mc squared is dimensionally consistent. So the solution is roughly 3 steps. First step, determine the units of each quantity. Okay. So what are the quantities in the equation? We have E, or the symbols, variable or symbols. That's what I mean by quantity, okay? Quantity, variable, symbol, in this context, they are synonyms. We have E, M, and C. Well, first is, what is the units of each thing? Now, energy is measured in joules, but 1 joule is kilogram meter squared per second squared. This is what it is in SI units. Again, the SI units, fundamental systems, right? Every single quantity in physics, if it has dimensions, the dimensions is represented, or the units is represented in one of the base units. Every single quantity. The units is one of these, it's not one of these, it's a combination of these 7 base units, right? So energy, which is joules, is actually a combination of 3 units, 3 base units, kilograms, meters, and seconds. That's 3 base units. Mass is a base quantity, right? The base unit is m, right, for meters. Speed or velocity, right? In terms of dimensions, speed and velocity are synonyms, right? C, the quantity C is actually speed. What is speed? What are the units of speed? Meters per second, right? So you say ms to the power minus 1. So once you have the SI units, these are the units. We replace the units with their dimensions. So like M, the unit has dimension L, kilogram has dimension M, S has dimension T, right? So that's what we're doing here. We're using our table here. That's the table, fundamental units above, to replace the units of E with the dimension. So the units of E was kg m squared s minus 2, but the dimension, we have the square brackets around it. And this is to differentiate the dimensions from the units, because somebody might see m here and think m is meters. You know what I mean? But m is not meters, m is the dimension of mass. Meters is the unit, the dimension is m. So that's why we put the square brackets around it. Also to show that we're not substituting a value for these things, right? So these are the dimensions of these quantities. Now, you look at the equation and you check the dimensions of both sides. So the left-hand side, which is E, is ml squared t minus 2. That's what I have here. But the right-hand side is m by c squared. So we need to multiply the dimension of m, which is m in brackets, by the dimension of c, all squared. So this dimension of c here, t to the minus 1. Sorry, this is minus 1, right? Multiply that all squared. So m by this all squared. So I mean, you just use the indices now and simplify it, and then you get m l squared t minus 2, which is same as the left hand side. So once both sides of the equations is the same thing in the same order, you know you're good to go. Typically, we tend to write it in alphabetical order. So this is not an alphabetical order. Yeah, alphabetical order will be L, M, T, but multiplication is commutative, right? It don't matter if it's M, L squared or L squared, M. It's the same thing. So the order is not important. What is important is the quantity, that the dimension, sorry, raised to the correct power, right? This example 2 is done even shorter, more quickly. Step 1 is, what is the unit of each of these things? We have 3 quantities, S, A, and T. The 2 is dimensionless, right? So we have S, A, and T. So for S, A, and T, the quantities or the variables, we need to figure out what the units. S is a distance or displacement, so the unit is meters. A is acceleration, so the unit is meters per second squared. Let's separate this a little bit to show that the 2 is for the S, not the M. And T in this equation is time. So the unit of time is seconds. So then we look to the table and substitute for M and S, right? What are the dimensions? M, the dimension is L. MS minus 2 is LT minus 2, and S is T. So we replace the unit with the dimension. That's how you know the dimensions of the quantities. Now replace each quantity in the equation with the dimension in square brackets. So I have on the left-hand side S. So the left-hand side is just L. Okay. What's the right-hand side? 80 squared over 2. Now we forget about constants. We don't need to divide by 2 on all these things, right? We have 80 squared. So we have A, which is LT to the minus 2. This is A here by T squared. So we have to square T. So that's why this capital T here is squared. When we multiply it out, we get L. The left is equal to the right, so it's dimensionally consistent. So I took some time to just give you a step-by-step process here, and hopefully this makes things a little bit clearer for how we do these types of questions, right? Using dimensional analysis to show that the equation is dimensionally consistent. So dimensional analysis, another big use of it is to derive formulas. Is used heavily in fluids and other branches of physics. This technique I'm going to show you all is the very, very simple technique. There's a more complicated techniques that, you know, are very involved that could help you determine very complicated formulas, right? We would be using it to try and derive formulas where it's a product of powers of quantities. Say it here, product of powers, right? Just a disclaimer, even though we could derive some formulas, it's kind of limited because You cannot use dimensional analysis to determine constants, dimensionless constants. So like if your formula have pi in it, or e, or √3, or a half, dimensional analysis can't really be used to find those things because those things don't have dimensions. These are constants. They don't have any units, and hence they have no dimensions. Therefore, they're dimensionless. That's what this means, right? They have no dimensions. We cannot use it to determine functions. For example, if your formula have tangent of an angle, right? An angle has units, is measured in degrees, right? But it still is kind of like a dimensionless thing. It's an arbitrary thing. Angles actually don't have any units in terms of the fundamental units, right? But the tangent of an angle is just a number. It have no units associated with it. So if your formula has cosine x or sine x inside it, dimensional analysis can't find that. You have to use experiments and more analytical methods, maybe geometry, the laws of physics, calculus, or all these other things could be used to help find those kinds of things. Dimensional analysis, believe it or not, is actually a very simple technique. Okay, a little complicated here, but it's the simplest of all the techniques in physics used to find formulas and determine things, right? So example one was this homework assignment from last class, right? We're continuing with dimensional analysis in lecture 21. This is lecture 21 here. Here we have the kinetic energy of a moving object, E subscript K. K, of course, being kinetic energy, as opposed to something as like potential energy, right? We say EP. So kinetic energy, EK, they say is proportional to a product of powers of its mass and velocity. So we don't know what the formula is EK is proportional to m to some power by v to some power, right? We don't know what the powers are, so you want to find it out. So determine the formula for EK in terms of FB and K. K is a dimensionless constant of proportionality, okay? So step one, we have to find the units of everything. So all the quantities we have M, V, and EK. K is not a dimensional quantity, have no dimension, so we don't worry about K. K is just K for constant, right? Not C for constant. EK is kinetic energy, is a derived quantity. We went through this before. These are the units for energy. Mass, base unit, so quantity is meters, and V is a derived quantity. The unit is meter per second, right? M over S, meter per second. That's step one. Step two, each SI unit here, we place it with its dimension. So what's the dimensions of kinetic energy? mL squared t to the minus 2. It's basically substituting m for kg, L for m, and t for S, right? That's kinetic energy. Dimensions of mass, m, dimensions of velocity, L t to the minus 1. Now here's where things get interesting. They say the kinetic energy is proportional to product of powers. Yeah, product of powers. So a product, these are is a product here, product of two things, and each thing is a power of the quantity, right? So is mass raised to some power by velocity raised to some power. We don't know what it is. That's why we have this proportional sign. Now, to change our proportionality to an equation, we have to multiply by a constant of proportionality, okay? And again, dimensional analysis cannot be used to find what K is. Experiments tend to do that, right? If you have an idea for a law or equation, you could use experiments to verify what that constant of proportionality is, okay? If you ever did labs in A levels, you would have done experiments where you measure the constant of proportionality for several simple equations, mechanical equations especially, right? Those things easy to measure. Substitute the dimensions for each quantity in this equation here. Do the equal sign. This is not an equation with a proportional sign, it is a proportionality. To change a proportionality to equation, I multiply by some constant K. We don't know what K is. K might be 5, it might be pi, it might be 1 over √2. We don't know what K is. Experiments will help us with that, but To change a proportionality type equation and multiply by a constant of proportionality K, which is what is said here, right? K is a dimensionless constant of proportionality. So good. We have an equation here. We don't know what A and B is, right? There's a formulate an equation where each quantity is raised to unknown power, right? So we raise it to a power because they tell us it's product of powers, right? So we don't know what A and B is. Then what we need to do is substitute dimensions for each quantity. So E has these dimensions here is to the power 1. That's the left hand side. On the right hand side, M is raised to the power A, so that dimension is M. And V has these dimensions raised to the power B. So we're doing dimensional analysis of this equation now, right? K is a dimensionless quantity, right? It's like 4, 5, it's just a number. So you could kind of ignore it here, right? So we simplify this, we get these powers here for each dimension. So we know this is the left hand side, M is raised to the power 1, but the right hand side, M is raised to the power A. We combine all the powers, okay? So then A had to be equal to 1, right? That way, this is the next step, equate the corresponding powers of each dimension. Similarly, on the left hand side, L is raised to the power 2, but here is L is raised to the power B. So 2 is B. So we don't find A and B already. Just to show it consistent, T on the left hand side is raised to the power -2, but T on the right hand side is raised to the power -B. But we know B is 2, so negative B is -2. This makes sense. This last one here makes sense. So it's consistent. So A is 1 and B is 2. That's this next step here. Solve for the unknown powers. A and B is 1, B is 2. And then write the equation in terms of the dimensionless constant of proportionality K and the powers of the quantities, right? So M is raised to the power 1, because that's where M was, right? Remember, M is raised to the power A, V is raised to the power B. So A is 1 and B is 2. So there's MV squared. KMV squared, right? So this is the equation we determined. They ask us to find the equation. The equation is E equals KMV squared. And it was kinetic energy. So we was kind of leaving out the K for kinetic energy, right? But we write it there and we have it there, right? So experiments show that the constant of proportionality is a half. So in physics, the formula for kinetic energy of a moving object is a half mv squared, right? But dimensionally, we could have proved that most of the formula, right? Dimensional analysis cannot determine the dimensionless constants, right? So this is, what is this, a 7-step plan I give you here, easy to follow. This how to take your time and you have to know your laws of indices, right? You equate the index of each dimension, you equate the powers of each dimension for each side of the equation, right? That's a crucial step here. And you might have a simultaneous equation, you never know. You might have you might have 2, 3, 4, several unknowns, but it tends to be fairly easy for simple equations, which is what we're giving you. I won't give you all anything too complicated, right? So what I want you all to do is try this example here. Centripetal force, FC, of an object moving on a circular object. They say the force is proportional to the product of powers of what? Mass, velocity, and radius. So we have mv and r. We have 3 quantities on the right hand side, mv and r, and we have a dimensionless quantity k, which you don't need to worry about. And that is equal to fc. So what's the units for force? What's the units for force? And then therefore what's the dimensions? Did we do that? Did we do any example with that? This was distance, acceleration, this was energy, right? So we could actually we could find that, right? Dimensions of force. look the give rate here, mlt to the -2, right? So it's possible to search for these things. Now the SI unit for force, right? The SI unit for force is the Newton. That's but in terms of the base units, right? In terms of the base units, 1 Newton is mlt to the minus 2. It's really mass by acceleration. Huh? Newton, if you remember Newton's laws, force is equal to mass by acceleration. This is acceleration, lt to the minus 2. Right, so you could find these things out, right? You could just say Newton unit, right? Wikipedia will bring it up here, right? Newton is the SI unit for force, right? It's defined as 1 kilogram meters per second squared. So you see here, SI base units, all you need is the SI base units. Once you have the base units, not the SI derived unit. The SI derived unit for force is the Newton, right? Symbol Newton. So we say a force at 3 newtons, right? But in terms of the SI base units, it's kilogram meter per second squared. So it's kg m s to the minus 2. So you could say that. Kilogram meter So the SI base unit for force is kilogram meter per second squared. I think we know what radius is. Radius is a length measurement. It's like perimeter. Okay. Velocity, we went through that up here, what velocity is, right? You see velocity is meters per second. And that's it, right? So try this question out and see how if you understand this topic. Okay, so we're gonna copy all these steps here and just change it up, right? Right. So determine the units for each quantity. So centripetal force. Centripetal force, force is a derived quantity, right? Measured in newtons, symbol N, which are base units, kilogram meters. So if you had to write it as a fraction, you would say kilogram meters second squared, right? This is how you would write it as a fraction. And this is how you write it as everything in the numerator, right? S is to the power minus. And this is mass by acceleration. Acceleration is meters per second squared, and mass is in kilogram, right? What we have m, so mass, this is mass m. We're looking at the quantities, the letters in the, what they tell us here. So we have m is base, okay. V is velocity derived quantity, meters per second, MSA minus 1, and R. So we need another one to put it here. Radius, R, is a distance and is measured in meters. Meters. Right? But we have mass. This is supposed to be kilogram. I don't know why I have this here. This is supposed to be kilogram. Right? Mass is in kilogram. Radius. Meters. Why I had that up here? Oh my goodness. I was wrong. Make sure and see. Mass is measured in kilograms, right? But the symbol is m, so that's probably where we get confused. So you could grab all of this. So let me see. So force. We want to convert each of these units here into SI units. So force is kilograms, which is M, meter squared, so that's L squared. It looks like something happened here. What went on? What went on here? It's solution 3, right? Right. So force is kilogram meter second squared. Mass is kilogram. Radius is M. Velocity meter per second. Right. So here, FC is kilogram is M, meters L, and S minus 2 is T minus 2. Dimensions of mass is M, capital M is the dimension, kilogram is a unit. Dimensions of radius. Radius is a distance, so that's L. And V is, this is L T to the minus 1. So all this look good here. So we're formulating an equation now. So I wouldn't say subscript C, I'm just gonna say F, right? So F is proportional to a couple of things. So I'm gonna say R here to the power B and V to the power C, right? And then we could just put a constant of proportionality here. So force is the product of these things: mass, radius, and velocity to some unknown powers. We don't know what these powers are, A, B, and C, but these are proportional. So to change it to equation, we multiply by some constant of proportionality, K, which is kind of what they said to do right here. Right? So, okay, step 1 looks good. Step 2 looks good. Now we substitute these dimensions here. So force, this L, this is L here, MLT to the minus 2, all to the power 1, is equal to K. So M to the power A L to the power B and LT to the power C, right? So this is V here, LT to the minus 1, you see it up here, LT to the minus 1, that's V to the power C. R is L, the dimension is L to the power B. And M, this is M to the A, right? So the left-hand side simplifies to this. M1, I should put 1 here, right? To the power 1. Always put the powers on the left-hand side. So M1, L1, T to the minus 2. Now here, this is MA, LB, right? And this is another L. we'll have an XL to the power C. You see this power C here distributes on the L, so you get L to the C, and T minus 1 by C is T to the minus C. So essentially, we have, we need to combine it. We need to combine it into single letters. So this is L to the power B plus C. Right? So M is A, T is to the minus C, but this L to the B by L to the C is L to the power B plus C. Okay. Now we create the correspondent powers. So for M, 1 is A. So we know A is to the power 1. For L, the left-hand side is 1, and the right-hand side is B plus C. Okay, remember, look at the left-hand side, L to the power 1, but this is L to the power B plus C. So 1 is equal to B plus C. And negative C is on the right-hand side, but negative 2 is on the left-hand side. So we have this situation here. Right? So therefore, what we could conclude here, we could say A is 1, C is definitely 2. And if C is 2, it means B is to the power negative 1. Right? B is equal negative 1. Right? So this first one says A is 1, this one says C equal 2. And if C is 2, right, then B plus 2 is 1. So you have to subtract 1, B had to be negative 1. So what we'll have FC R to the power negative 1, right? So this is what? I could write this as some constant by, we'll use a fraction, something like that, mv squared over r, right? When you write mv squared, the squared is just for the v. If it was mv all squared, you would probably write something like this. This is just normal mathematics I'm talking about here. If you want both the m and the v squared, you would write that, but that's not what we have. We just square in the v, so we just put the m next to it. Now experiments show that the constant of proportionality is actually 1, you know, right? So centripetal force in physics, centripetal force is just mv squared over r. Okay, there's a formula here. So you would do experiments to find out what the constant of proportionality is, like plot a graph of k versus v squared or something, knowing the mass and the radius, and the gradient of the graph could be k. If it's a straight line through the origin of gradient 1, then you know the constant of proportionality is 1, right? So, but you have to do that via experiment. Dimensional analysis brought us very far, right? It told us the centripetal force is mv squared over r by some number. If that is a formula, if it is really a formula, we don't know if it's really a formula, but this is an actual formula in mechanics. The centripetal force of an object moving in a circular orbit is mv squared over r. R is the radius of the orbit, m is the mass, and v is the velocity, tangential velocity of the object, which is the object velocity perpendicular to the radius at any point in time. This is an actual formula, right? Watch this, centripetal force on Wikipedia, right? It's really dv/dt. It says calculus, right? The rate of change momentum in a sense, right? You see it here, mv squared over r. Magnitude of the centripetal force. See, there's the tangential speed here. There's the speed at right angles to the radius. Yeah. But this formula here, mv squared over fc. You see, I didn't make this up. So I hope you all understand this. I added a little bit of notes here for step 4. When after you substitute for each quantity in terms of the dimensions, express each dimension to a single power on both sides of the equation, right? To a single power. So you see here it was easy. L was a single power B, L is a single power 2. So hence B is 2. That's why we say B is 2 for L here. But lower down, right? Step 4, again, single power. Express each dimension as a single power. So here we have 2 L's. We need to express L as a single power B plus C. That's how we got B plus C on the right is equal to 1. As this B plus C equal to 1 here, right? So I think these notes are very good to help you understand what to do, which is you're trying to do. The hypothesis is that you have some equation is always going to be product of powers. That's what simple dimensional analysis is, with a constant of proportionality. We usually call it K, right? Bear in mind that the other quantities in the equation shouldn't be K. It shouldn't have nothing called K other than the constant of proportionality, right? So be careful of that. But the idea is you're going to assume some equation, right? F force is, well, you multiply everything. If you're multiplying everything together, then, you know, these powers how to relate to each other somewhere using simple mathematics. And it's just using simple indices, the laws of indices. L to the A by L to the B, sorry, L to the B by L to the C is L to the B plus C. And then B plus C is equal to 1. Because again, express each dimension to a single power, right? Once you do that, it's fairly straightforward what each letter is, and you substitute and you get the equation. You wouldn't know what the constant of proportionality is. So this is your final answer here. See this part here, FC is equal to KMV squared over R. This is your final answer. It had to be an equation and it had to have K in it. And you have to say K is the dimensionless constant of proportionality, okay? That's really all it is to this topic. This is the meat of the matter. This is really what I wanted to teach you in dimensional analysis. How to prove, how to arrive at a formula. The stuff we did before, which is verifying a formula, this was a precursor, right? This shows you how to verify a formula that it's correct. We're using this technique here in a sense to arrive at a formula. In this usage of dimensional analysis, we know the equation and we're just showing that the dimension is consistent. The actual usage I want to show you of dimensional analysis is deriving a formula. This is what will come in your assignment, being able to derive a formula. So here you don't know what the formula is and understand it have limitations, right? But you could reach a good distance with dimensional analysis. And this is why it's so powerful. It's such a simple technique that is very powerful in physics for when you're trying to understand a law or how quantities relate to each other and how they may behave, right? You do dimensional analysis to test your assertions, to test your hypothesis, right? Actual experiments will have to be conducted to see if really the centripetal force depends on V squared or if it's inversely proportional to R, you know? Actual experiments will have to be done to see if this is an actual equation. This is not how you just prove an equation and come with an equation out of the blue in physics, right? If you look at all the equations in physics, they took many years to come about, a lot of research, a lot of experiments, a lot of physicists actually work on the problem before coming up with a formula. A formula is not a jokey thing, right? It's a serious thing. It takes sometimes several hundred years to come up with a formula. This formula here, this formula E equals mc squared that Einstein came up with. This formula came around in the early 1900s, like 1905, right? That's more than 100 years ago, right? What was happening all these centuries before that? The centuries before that, nobody knew this formula existed. They didn't even know how to measure the speed of light correctly. Fowler's putting it in a formula, right? This formula, the birthday of this formula is 1905, somewhere around there, when Einstein published it, right? So all the years before that, 1905, this formula didn't exist. Physicists didn't know about this. So coming up with a formula is not just dimensional analysis. It's not like what we do here. This is just guide you and test your hypothesis that maybe it's v squared, you know. Somebody might say, I think it's v cubed, you know. It's no, we do dimensional analysis. If it's v, it's v squared. If it depends on v, it's v squared. If it depends on r, it's inversely proportional to r. You know, dimensional analysis gives you an idea what is happening, but this is just a precursor to a long line of effort with several people and experiments to come up with a formula. I hope you all understand what I'm talking about.